Good morning, everyone. So welcome to my YouTube channel, Math Sutra. So today we are going to see lecture on functions of bounded variation. Till now, if you have not subscribed my YouTube channel for this type of interesting topics, subscribe it immediately. So let's start today's session now. Okay. Today we are going to study variation function corresponding to a function of bounded variation. Okay. Let's see how it is defined. So what is variation function? Variation function, or you can say total variation function, same thing. So I am saying variation function. Let f close interval ab to r be a function of bounded variation. Okay. Now we know that if a function is bounded variation, you take any subinterval of closable AB, then function is also function of bounded variation on that subinterval. We have seen this theorem in last lecture. Okay. So given for each x belongs to closed interval ax ab, the function f closed interval a to x is also function of bounded variation. Okay, we define because if function is bounded variation, this value total variation of f over closed interval ax, this will be a finite value. So we define I am taking f in base x is equal to this. Okay. Then bf closed interval ab to r is a function, and okay, this function is called so this is for each x belongs to closed interval ab. So this is a function. This function is called variation function, or you can say total variation function. Total variation function of f or corresponding to f. There are two names. So given a function of bounded variation, we can define variation function corresponding to f. Okay, f is function of bounded variation. Okay. So what are the properties of this function? Properties of variation function. Properties of variation function. Okay. First of all, you see that BFA, what is this? This is actually 0. Why? First property is this. Why? Because BFA is nothing but BFAA. So if I am on same point, whatever partition I will take, that will be x0, x1, x2 will be that one will be A. So their difference will be give you functional value same. That is why it is 0. Okay. So this implies okay. So second one is second property. If F is monotonically increasing function, then variation function of this is nothing but equal to F minus F6. Okay. In particular, if FA is equal to 0, then BF is equal to nothing but F. So its proof, let's see its proof. It is given that F close interval AB to R is a monotonically increasing function. Okay. So in this property, you write if F is monotonically increasing and FA is equal to 0, then VF is nothing but F. Okay, that is we are asking. So it is given that function is a bounded variation. Okay. So this implies F close interval A to X is also monotonically increasing for each X belongs to close interval A. And we know that monotonically increasing or decreasing functions are functions of bounded variation. Okay. And the total variation is given by, so what will be BFX? This will be BFAX. Because every monotonically increasing function is function of boundary variation, and its total variation is given by this fx minus fa. Absolute value will become, but it is monotonically increasing, so fx will be greater than fa. So absolute value will not affect anything. Okay, so this implies bf is equal to f minus fa. It is okay. For each x belongs to closing column A. So this implies this. Now, additionally, now if f also satisfies fa is equal to 0, then what we will get? Then this will be bf is equal to f minus fa will be 0. Okay. So now it is going to be okay. This. Now third property is that if f is monotonically decreasing, then bf is nothing but fa minus f function. Okay. fa minus fa. In particular, if f is monotonically decreasing function with fa is equal to fa is equal to 0, then bf is nothing but negative of f. Let's prove it. Now, f close interval ab to r is monotonically decreasing. So this implies you take any close interval af, it is also monotonically decreasing for each x belongs to closed interval AB. Okay. So this we know that monotonically decreasing function or monotonically increasing or simply say monotone. Monotone subword include both the meaning monotonically increasing or decreasing. So monotone functions are functions of bounded variation. Monotonically decreasing is functions of bounded variation. Okay. And its total variation is given by, so how it will define, it is given by this, it is given by B, sorry, it is given by FA minus FX. Okay. That is BFX. for each x belongs to closed interval AB. Okay. Now, what is this? Simply, this implies BF is nothing but FA minus F. Now, if F also satisfy FA is equal to 0, we get what we get? You just FA is equal to 0 in place of FA. Okay. So BF is equal to minus 0 F. This implies BF is equal to minus F. Okay. So fourth property we are going to see. Fourth property. BF is, it means variation function. BF is monotonically increasing function. Increasing function. Okay. Therefore, BF is nothing but BF. Proof. So let x1, x2 belongs to closed interval AB such that x1 is less than x2. Then what is AX2? This is AX1 union X2. Okay. Now F closed interval AB to R is a function of bounded variation. So this implies it will be on subinterval AX2. R is a function of bounded variation. Okay. Now F is function of bounded variation in AX2 and X1 is in between. So what does it mean? FB AX2 is equal to BF AX1 plus BF X1 X2. Okay. Because X1 lies in between A and X2. So F will be functions of boundary variation over AX1 and X1 X2 closed intervals. Okay. So this implies, what is this? BF AX2 minus BF AX1, and that is equal to BF X1 X2. Okay. So what is this? What is this? I can write it BF X2. And what I can write this? BF X1. That is equal to BF, and we know that variation is always non-negative. So this is non-negative. Okay. So this implies BF X2 minus BF X1 is greater than equal to 0. It means BF X2 is greater than equal to BF X1 for X1 X2 belongs to AB with X2 greater than X1. Okay. So what does it mean? It means BF is monotonically increasing. Okay. Now BF is monotonically increasing. Now BF is monotonically increasing by property 2. We have what we have? By property 2 we have BF X is equal to nothing but BF X minus BF A. But by property 1 we have BFA is 0. By property 1 BFA is 0. So put the value of BFA. Zero. So this implies, so BF X is equal to BF X for all X belongs to the interval AB. This implies BF is equal to BF. So this is proved. Okay. So we have proved the property 4. Okay. We have proved the property 4. Okay. Now 5. BF plus F and BF minus F are monotonically increasing functions. Okay. Let's see its proof. Okay. Monotonically increasing functions. Let x1, x2 belongs to closed interval AB. We have proved in the proof of property for that so here with x1 is less than x2. In property or we proved property so in the property for we have property 4 we have proved that we have proved that VF x2 minus VF x1 is VF x1 x2. Okay, we have proved it, but we know that this is nothing but this is less than SP of F x1 x2, but SP is always less than F x2 minus F x1. Okay, this part we have already proved in property core, but we know that SP for any partition P of closed intervals AB x1 x2 closed interval x1 x2 we have this one, and and we have that SP is always greater than difference of f1 minus f1 x2 minus my absolute value of f x2 minus f1 f x1 absolute value. Okay, for where P is any partition of closed interval x1 x2. So what we have, this implies VF x2 minus VF x1 is F x2 x1. Okay, okay. By this But we know that when absolute value have, then it will be fx2 minus fx1, because plus minus of any number is always less than equal to absolute value of that number. So we have this one. Okay. Okay. Now let's say equation number. So what we have actually? This implies bfx2 minus bfx1 is greater than plus minus b f fx2 minus fx1. Okay. So bring this side. So if we will bring this side, it will be bfx2 minus bfx1 plus minus, or you can take minus plus plus will become minus and minus will become plus. fx2 minus fx. So this implies bfx2 plus minus fx2. Okay. Minus bfx1 minus plus fx1. Okay. So what is this? This implies bf plus minus fx2 minus bf minus plus fx1. Here it is minus plus. Minus. So let's see question number 1. Taking positive sign, we get, what we get? Bf plus fx2 minus bf plus fx1 is greater than. This implies bf plus fx2 bf plus fx1 for x1 x2 belongs to A B such that x1 x2 is greater than x1. So what does it mean? It means bf plus f is monotonically increasing on AB. Okay. Monotonically increasing on AB. Now taking minus sign, minus sign in 1, we get so what was the equation 1? So we are here in starting we have taken plus sign in 1. So from 1 we are taking plus sign. So taking plus sign from 1, we have proved that BF plus F is a monotonically increasing. Now we are taking negative sign from 1 and we will prove that BF minus F is monotonically increasing. Okay. So take negative sign from 1. Okay. We get VF minus F x2 minus VF minus F x1 is greater than 0. So this implies VF minus F x2 greater than 0. VF minus F x1 or x1 x2 belongs to closed interval AB such that x2 is greater than x. So what is the meaning of this? This implies VF minus F is monotonically increasing. So this implies VF minus F is monotonically increasing on closed interval A. So finally, we have proved, it is proved that BF plus F and BF minus F are monotonically increasing functions on closed interval. Okay. So today's lecture up to this. Okay. If you have any problem related to this lecture, you can comment me on my YouTube channel. Okay. So in this lecture, we have defined, I am recalling what we have done. We define variation function corresponding to a function of bounded variation. And we have proved, we have studied 5 properties of variation function, that at A, VF is 0, and if you have a monotonically increasing function, the VF corresponding to it is nothing but F minus F is. If it, and in particular, if F is equal to 0, VF becomes F for such monotonically increasing. Third property is that if F is monotonically decreasing, VF is equal to Fa minus F. Okay. In particular, if monotonically decreasing function have Fa to 0, then VF is equal to minus F. Fourth property, we have studied that the variation function is actually monotonically increasing function. Okay. Okay. In fifth, we have, so it in fourth property, VF is monotonically increasing. By using, so we have V of VF is equal to VF minus VFA, but VFA by property value it is 0, so VF, V of VF is equal to VF. Okay. So in fifth property, we have proved that VF plus F is a monotonically increasing and Bf minus F is also monotonically increasing function on closed interval A. So today's lecture up to this. If you feel any problem, you can comment me. I already told you. So thank you very much for today's lecture. Like, share, comment and subscribe my YouTube channel. Thank you very much for today's lecture. Thank you very much.